So statement of this theorem is if G is a Hamiltonian graph, then number of components of G difference S is always less than or equal to cardinality of S, where S is a non-empty subset of vertex set of G. So to prove this theorem, we are assuming G is a Hamiltonian graph and S is a non-empty subset of vertex set of G. So we are considering these two. Now we are going to construct a new graph G difference S. That is, we are deleting all the vertices of S from the graph G. Then this graph G difference S may be a disconnected graph. Our aim is to prove number of components of G difference S should be less than or equal to cardinality of S. By our assumption, G is a Hamiltonian graph. Therefore, G contains a Hamiltonian cycle, namely C. That is, C contains all the vertices of G exactly once except the starting and ending vertices. Since G is a connected graph, there must be edges connecting vertices of G minus S with vertices of S. So we are considering the set F, which are subset of edge set of C, that is E of C. So F is nothing but collection of edges from the set E of C. What is the speciality for this F means? This F join a vertex of G minus S and a vertex of S. For example, suppose our components of G minus S are denoted in this part and vertices of S is noted in this section. Then a vertex of S is joined to a vertex of G minus S through one edge, namely an edge of F. So likewise, we are considering that set F. So here clearly every component of G minus S is incident with at least two edges of F. Because if we start from S, then through this edge of F, we can reach G minus S. Afterwards, we can't use this vertex to come to S because C is a Hamiltonian graph. So each vertex should be used only once. So to reach the set S, there must be some more vertex in G minus S which is joined to vertex of S through this edge of F. So we can conclude every component of G minus S is incident with at least two edges of F. So cardinality of F is counted, then it should be greater than or equal to 2 times omega of G minus S. That is, these omega of G minus S are counted 2 times, and comparing with cardinality of F, that cardinality of F must be greater with that value. Also, since C is a Hamiltonian cycle, every vertex of G is incident with two edges of edge set of C. So since it is a cycle, every vertices are incident with only two vertices of edge set of C. In particular, every vertex of S. So S is nothing but a subset of V of G. Is incident with at most two edges of F. This F is nothing but a subset of edge set of E of C. So why we are using at most two edges means it may be one edge, two edges of F or zero edges of F. Here this vertex S is not joined with any F edges. So it may be possible every vertex of S is incident with at most 2 edges of F. So in this connection we have cardinality of F is less than or equal to 2 into cardinality of S. That is, we are counting all the edges of all the vertices of S and comparing with the cardinality of F. 2 times we are multiplying this one, then we get cardinality of F is less than or equal to 2 into cardinality of S. So using 1 and 2 we can conclude our omega of G minus S is always less than or equal to cardinality of S for all S's contained in V of G.